Have you ever tried to give someone directions? You can't just say go 5 miles. You have to say go 5 miles that way, right? Well, that simple idea, that combination of distance and direction, is the key to the entire world of vectors. Today, we're going to build your complete toolkit to help you master them.
So let's start with a really simple question. Imagine you walk 5 kilometers, okay? That's just a distance. But what if I told you to walk 5 kilometers northeast? All of a sudden, you need more than just a number. So how do you actually describe that? How do you package up both of those things, distance and direction, into one neat little instruction?
Well, the answer is a vector. It's a fundamental concept in physics, in math, and it perfectly captures any quantity that has both a size, which we call magnitude, and a very specific direction. It's like an arrow that knows exactly where it's going.
So here's our game plan. First, we'll nail down the basics of what a vector is. Then we'll get into adding and subtracting them. After that, I'll show you a real pro-level technique using components. And finally, we'll cover some advanced properties to really round out your toolkit. Let's jump right in.
All right, first up, what exactly is a vector? Let's get our hands on this basic but super important tool. Okay, there are a couple of really core rules you gotta know. First off, and this is a really powerful idea, a vector's location doesn't actually matter. I mean, you can pick it up and move it anywhere in space, and as long as you don't change its length or the way it's pointing, it is the exact same vector. Pretty cool, right? Second, you've got to compare apples to apples. You can't just go adding a force vector to, say, a velocity vector. The units have to match up.
Okay, let's grab our power tools, adding and subtracting. We know what a vector is, but the real magic happens when we start combining them. This is where they get super useful.
So this slide shows the two main ways you can add vectors just by looking at them. Over on the left, you've got the head-to-tail method. Think of it like following a treasure map, right? You follow the first arrow to its tip, and then from that exact spot, you start following the second arrow. The final result? That's the shortcut, a brand new vector that goes from where you started all the way to where you ended up. Then on the right, we have the parallelogram method. For this one, both vectors start from the same point. Then you kind of complete the parallelogram shape. The sum, the final answer, is the diagonal that cuts across it. And here's the most important part. Both methods get you the exact same result. They're just two different ways of looking at the same thing.
And this brings us to a super important takeaway. It's just like how 2 plus 3 is the same as 3 plus 2. With vectors, a plus b is the exact same thing as b plus a. The order you add them in, it just doesn't matter at all.
And we can see that same idea in action right here. It doesn't matter if you group A and B together first and then add D, or if you group B and D first and then add A. You see? You end up at the exact same final point. How you group them makes absolutely no difference.
So what about subtraction? You might be thinking, oh great, a whole new set of rules to learn. But nope, there's actually a really elegant little trick we can use that just builds on what we already know about addition.
So check this out. This is the trick. To calculate a minus b, you don't need some new fancy method. All you do is find the opposite of vector b. That's just a vector with the same length, but pointing in the complete opposite direction. And then you just add that new vector to a using the same old head-to-tail method we just learned. So really, subtraction is just addition in disguise. Pretty clever, huh?
All right, we've got the basics down pat. Time for the pro move, working with vector components. I'm telling you, this technique is the key to making even the most ridiculously complex vector problems simple.
So here's the big idea. We can take any vector that's pointing off in some diagonal direction and, well, we can break it down. We can split it into two separate, much simpler vectors. One that points purely sideways, that's its x component, and another that points purely up or down, that's its y component.
Okay, so how do we figure out the exact lengths of those little component parts? Well, this is where a little bit of high school trig, SOHCAHTOA, comes in super handy. If you know the angle of your main vector, you can basically treat it like the hypotenuse of a right-angled triangle. The vertical part, Vy, you can find using sine. And the horizontal part, Vx, you find using cosine. This lets us swap a tricky diagonal arrow for two nice, clean numbers.
So, why bother with all this? What's the point? Well, imagine trying to add 3 or 4 different diagonal vectors together. It would get super messy, right? You'd be stuck using complicated sine and cosine laws. But if you break each of those vectors into its simple x and y components first, the problem turns into basic arithmetic. Seriously, you just add up all the x parts to get the final x part. Then you add up all the y parts to get the final y part. It's a total game changer.
Okay, time to really master this toolkit. Let's look at a few final advanced properties. These are the concepts that show you just how powerful and, well, elegant this whole vector system is.
This is a really cool one, scalar multiplication. Now, a scalar is just a fancy word for a regular old number, one that doesn't have a direction. When you multiply a vector by one of these scalars, you're basically just changing its length. So multiply by 2, the vector gets twice as long. Multiply by 0.5, it shrinks to half its size. And get this, if you multiply by a negative number, like -3, it not only gets 3 times as long, but it also flips and points in the complete opposite direction.
And that idea leads us straight into what we call collinear vectors. It's actually pretty simple. If you can take one vector, multiply it by some scalar, and get a second vector, then those two vectors are collinear. It just means they're parallel to each other, they lie along the same straight line.
And this, right here, is where it all comes together. We can now combine all the tools we've put in our kit, addition, subtraction, scalars, components, to solve much more abstract problems, and even prove things. Like, take a look at the proof on this slide. It uses vector pathways to show a geometric relationship. We don't have to go through every single step, but it's a great example of how vectors can give you these really elegant solutions to problems that would otherwise be a huge headache.
Okay, to wrap things up, I'm going to leave you with a little challenge. Let's say you have two vectors. We'll call them u and v. When would the length of their sum be greater than the length of their difference? What about when they're less than or even equal to each other? The hint is right there on the slide. It all comes down to the angles between them. Try sketching it out. Use that parallelogram rule we learned earlier. It's a fantastic way to really test out your new vector toolkit.